All right. I have my setup ready in my office, and I'm here to finish recording the Chapter 4 lecture that we didn't finish in class so that you guys can take your exam in the next few days. So that brings us to the first thing. Over on our Canvas page, now I've added the quizzes button. You can get to the exam or the homeworks. Both of those are quizzes in Canvas's terminology. You can get there through the syllabus, through the assignments, or through the quizzes. I'm going to go through the syllabus. So on the syllabus, it's going to have grayed out all the things that have already been due. So your homework 4 is due still Monday, and the exam is due on Tuesday. Now, you can turn either of these things in before. I highly suggest you turn in the homework before you take the exam, but they're both there. So if you're going to take the exam, when you click on the exam, I put some information up here. So this is going to close at midnight on Tuesday, January 28th. You can take it anytime between now and then, as long as you have a strong and stable internet connection. You'll want to be in a room by yourself or a closet. You need to have good lighting. You're going to need to be able to use Chrome as your browser and install the little extension that will take control or be able to record your screen, your webcam, and your mic. You need to have access to all three of those. You'll need to show your ID to the camera. There's a place for that. All the instructions will be on screen. The very first thing, it asks you to close all other windows besides the Canvas, all the other tabs in your browser, all the other programs you have on your screen. But I wanted to show you what it looked like so you knew beforehand. So the instructions will come up, and here I have some screenshots. I put together a little page here that's linkable, that this is what it'll look like. So if you go in on Chrome, it'll ask you to install the extension, then it'll give you some instructions. It's called Procterio. So it will, if you click here, it will actually close all your tabs for you, or you can close them individually. If you lose internet connection, it'll close and submit the quiz or exam, and that's it. So you want to make sure you have stable connection. If anything like that ever were to happen, please email me, and this time Tyson Barrett. I have his email for you for handling those funky things that happen once in a blue moon. So just so you know, it will close out your browser when you're done. And if you have two screens like I do here, you have to unplug one of them so you only have one screen. If you're on a laptop, you don't need to worry about that. So you need to close all the tabs, and you cannot right click on the exam, and you can't print it out while you're taking it. The Procterio will collect information from your mic, your webcam, your physical location geographically, your identity with your little card, anything that's on the clipboard that you copied and pasted, you can't access anymore, but it will copy that. It will know the size of your browser. If anything does get opened up, it videotapes and monitors your head, your eyes, your mouth, everything that's on your screen, any website you were to visit, it records all that. Any programs or applications that are running, or anything that is displayed on the screen. So just so you know, this is just, the pro is you get to take this in your own convenient location and time, but the con is you have to give us the Procterio program all this information through your computer. So it'll ask you to install and set up some things. Just allow anytime it asks. Yes, share your screen, and then once it gets access to your webcam, it'll bring up this little place where you hold your card up to the camera, and it will take a snapshot. So that's how you prove it's you. And then it will give you, after it goes through all the diagnostics, it'll give you, warning, you're going to take your exam, go to the bathroom, get water, get comfy, whatever you need, get ready. Because once it starts, you have 2 hours until it's submitted. Whether you submit it or not, at 2 hours, it's over. You cannot close it and come back later. So be ready. I did make it a 2-hour window once you open it, but I'm anticipating should take a mean time of 20-ish minutes. I'm hoping most everyone within a half hour. If it takes you more or less, I wouldn't get concerned. For some people, this is going to be more review. Other people, it'll be starting how much detail there is, but I don't think so. There are 11 questions. And again, I'm not out to make you have to race to finish it. I'm not going to ask you to code. I might show you some output and ask you to write it out, what it means, how you would write it in APA format. Definitely could be some of that. So there's the exam ready to go. So you can use your textbook, if it's the hard copy, the paper copy, any notes that you printed out, either handwritten or computer printed out, that could be your chapter summaries, slides from the PowerPoints, anything that you wrote for part of the homework or for the notes. You can use a handheld calculator that cannot send and receive information. You cannot use a cell phone, a tablet, or a computer calculator program. But basically, you can have any papers with you, physical papers. What you cannot have is anything electronic. No electronic textbook, no electronic notes, no electronic homework, no websites or online anything. You cannot bring up the calculator on your screen. You cannot contact any other person, living, distance, recorded, anyhow, this is you. So trust you guys, your grad students. So again, you are going to need your ID, any kind of identification, driver's license, Utah state card, etc., and be able to install that Chrome extension to access your webcam and mic. So good luck. I know you guys are going to do great. So back to our homepage, which looks a little different again. So now there should be 4 of these little hexes. The first one is my picture. This will take you to my website in case you ever want to go to my personal website. The second one that says Stat Foundations, this is for our course. This is the one that has the notes, and we'll go there. The encyclopedia that has examples of how to do the things in the homework, and then our YouTube. So I'm going to go to YouTube first. If you click on it, and I'm going to right click to open a new window. Our YouTube, Sarah Schwartz Stats, we now have 2 playlists. If you go into the playlist, I have this is interesting. We have the first playlist is our in-class lectures. So there are 2 of those showing up there. They're our last 2 lectures. And then this new playlist that I just added yesterday has 3 videos here that other people produced that I thought were the best of the best that I could find online about the central limit theorem and sampling distribution for the mean. And these range from 3 to 9 minutes, so pretty short. I just added 4 more that are on p-values. What is a p-value? Because we're using normal curve and shading area, we're doing this to come into inference, and that's the p-value idea. This very last one, this man with the what is a p-value in white over the top, is really good. It's 9 minutes. And then this gal with the shorter hair, hers is phenomenal, and it's only 3 minutes. And rather than redo it, I thought I would just link those. So those are some good resources to kind of look over, watch if you have a couple minutes. Again, none of them are longer than about 9 minutes, some as short as 2, but those are some good resources for you. This recording I will put on another playlist that will be recordings Sarah made in her office or something like that. So that's the YouTube. I'm going to pull up the encyclopedia next, again in a new tab. I'm going to go to the volume links. And we are in, let's see, exploring, creating new variables. We're not going to do a lot in chapter 4, but this is how you would get to, like here's the explore unit and doing bar plots, histograms, box plots. So there's examples of doing all of these here, doing by separating by a factor, by color, by the x-axis, by paneling, doing multiple things, color and staged, having 2 categorical variables to split by. So there are different examples using various data sets, sometimes using Eno's data set, sometimes using this cancer data set or another data set, how to do all the things that we're learning about. So now Stats Foundations. This is our course website, and this is pretty much the same. I added the links to the textbook. This is supposed to be dollars. I'll need to change it. And the volume links we use the most, and our YouTube channel. So I added some links here. Here's our table for our lecture slides. So right now we're going to finish going over chapter 4. Open that up. Here we go. So chapter 4. This is what we started in class last time. So I'm going to skip all the way to when we go to slide 25. Intro back into the theory of modeling again. So this is the core that you need to get out of this chapter, if anything, is the idea of inference. So in this blue larger boxy area, I have colored in blue, it says population. Any numbers that apply to the entire population are parameters. That's the sample size, capital N, the mean, mu, variance, sigma squared, and plain sigma is standard deviation. All of those numbers, if they apply to the entire sample, all members of the population, they're a parameter. And we usually use the Greek letters a lot of the time. Inside of that blue population, I have this green egg-shaped oval. This is a sample. A sample is a part of the population. Any number that applies to the sample is a statistic. We got these letters matching, that's nice. So we use lowercase letters a lot of times and regular letters instead of the Greek letters. We can have an average or a mean that applies to all of the members of the population or just to the members that are in our sample. So when we're going to do inference, statistical inference, that's when we take information about that we get off the population, or off the sample, so a sample statistic, and we're going to draw a conclusion or make a statement about the wider entire population. So this is the main idea, is the idea of a sampling distribution. And again, there's those other videos to go through. They have some illustrations that can be helpful if this is something that isn't sinking quite yet. This is backwards than what we usually do. For a sampling distribution, we play the role of being a god, that we know the truth. We know that the population in its entirety looks like this. And we think about drawing a sample over and another one and over and another one and another one and another one, and try to think about what all of the possible samples could look like if we knew this truth about the whole population. Now, then chapter 4, we are coming from this direction, that we know the whole population. What would samples look like if we took many samples? That's the idea of the sampling distribution. What is the center and spread going to be like if we took a lot of samples? In real life, which is going to start in chapter 5, we flip that and say, we only know one sample. What can we say about the wider population? So in chapter 4, we're going to, be backwards. We're going to say, we know the whole population. What would samples look like? And that's the idea of a sampling distribution. So there's this idea of a random variable. Each sample is going to be a little different than the one before, the one after it, because of randomness. It's this idea of sampling has some stochastic process or some error or some wiggle room in it. So the law of large numbers tells us, and this is a law, like the law of gravity. It's not a postulate, it's not an idea, it's not a hypothesis, it's a law. The law of large numbers assures us that if we measure enough subjects, a large sample, then the sample average will be close to the population average. If I wanted to guess at the population average, my best guess would be the average of the sample. Is it going to be exact? Probably not. It's probably going to be some margin of error, but it's our best guess. So there's a shiny app here, and I'm going to not go over it right now, but I'm going to go to the next slide first. The sampling distribution for the mean. So if I was to know the whole population and take a sample, I could calculate the sample's mean. I'm going to set it aside. Then I can draw another sample, calculate that average, put it aside. And over again. And if I was to look at all possible sample averages, what shape would that histogram be like? So this green box says if we have individual observations, one at a time in the entire population, so one at a time individuals in all the population, that average is mu, and the standard deviation is sigma. If I take a sample now on this yellow arrow, it says SRS. That stands for simple random sample. It's the idea that all these statistical tests we're going to learn about are based. A simple random sample. Generally in real life we have a sample with some level of convenience in it, but we treat it if it's truly just a random sample most of the time. And little n is the size. So if we were to take these samples from our larger population, the sample average should be close to to the population average. In the long run, they would be exactly equal. The spread, however, in terms of standard deviation, would not be the same. The average of the averages would be the average. Averages are the same. The average of all sample averages is the population average. The mean of sample means is the mean of the population. The spread, the standard deviation, if I have one standard deviation for all individuals in the whole population, if I do sample averages, the spread will be less. And not just any amount less, it'll be whatever the population of individuals was divided by the square root of the sample size. So, if we know we have a population, here in green it says of all possible individuals, and it says n, and then in parentheses, mu sigma. That is a way of statisticians being lazy of writing normally distributed with the first number is the mean and the second number is the standard deviation. So this little green box here says if, again, we're God and we know this, if all the individuals in the entire population together have a normal distribution with a center, mean equals mu, and a spread, standard deviation equals sigma, if we were to, from that population, draw out repeated samples, all of them size n, the sample averages, the sampling distribution, would also be shaped normal, would also have center mu, but its standard deviation spread would be sigma divided by square root of n. This is the standard error. So standard deviation is the spread in the whole population. If we do the spread in the sampling distribution, the standard deviation of sample averages, that is called the standard error for the mean. Sometimes it's abbreviated SEM, sometimes just SE. So it's whatever the population standard deviation is divided by square root of n. So if our whole population is normally distributed, the sampling distribution for sample averages is also normally distributed, exactly. But what if our whole population wasn't normally distributed? What if it had a shape that was skewed, or had some kurtosis, or was bimodal? What would the sampling distribution look like? Well, here we have an example that is looking at the length of customer calls, service calls to a bank. And a lot of these calls are short. So if we look at the distribution of all individual calls in the entire population, this distribution is very skewed. There's a lot of short with the floor being 0, can't have negative times, and trickling up to higher numbers for those hard cases. That's a skewed distribution for all individual calls. Now, sometimes when you're doing a homework or a test problem, you have to read between the lines. If it says the mean of calls, could you replace the mean of all individual calls? Then it's the population. Now, if we were to take a sample, now in this day and age, we can very easily hold a record of all possible calls, but for a second, think we only could draw a sample of all possible calls. The average of all the averages would be the same. So this first distribution, that's the population that's very skewed, it has a certain mean, and I'm going to guess it's 180 minutes. If we go to this second one, which is we have a sample size 80, the average, that mean, will be the same for the sampling distribution as it is for the whole population. For samples size 80, the difference is whole entire population of all individuals versus all samples size 80. So the center remains the same. The thing that changes is the shape. It goes from being skewed or bimodal or J-shaped or anything else. If we take enough samples that are big enough, the shape of the sampling distribution will become more normal-ish. And because the spread shrinks, and the amount it shrinks is whatever the spread used to be, standard deviation sigma, divided by the square root of the sample size 80 in this case. So here we have a J-shaped, very little more than skewed original distribution. So the population distribution you could think of as all individuals. So it could be all sample size 1. So if you ever have a question on a homework or an exam like this that asks about a person or all people, one individual or all people, that's when you're dealing with a population. The other kind of problem or question would ask if you're dealing with a sample size, and then we'll have to give you a size of the sample. Then you know you're doing a sampling distribution. So here's the central limit theorem. If our population of all individuals has any shape, if we take samples, the sampling distribution, not the population distribution, the sampling distribution will have the same mean but smaller spread and will be more normally shaped. So here's this first one. These are sample size, this panel B are sample size 2. Already we're seeing that our distribution is becoming less skewed. And down here in this lower corner, we'll move over to sample size 10. It's shifting more normal. And then this last one, panel D, should be sample size 20. This is an error. It's becoming even more normally distributed. So when we take samples from a population, no matter what the shape of the population, the sampling distribution for the mean will be normal. Now this is only sample size 20. It's normal, it becomes more normal, but it doesn't really take that big of a sample till it gets really close to normal. And this is why our stats tests that rely on normality work, even if our distribution of our variables are not normal. Because even if a variable is not normally distributed for all individuals in a population, if we're looking at the average from a sample, that is going to be more normally distributed. So in languaging, in words, in verbiage, this is very convoluted the way we say it. When a sample size is large, how large? Well, we'll get that in a second. When a sample size is large, the sampling distribution for the mean is approximately normally distributed around the same mean that the population had, but with standard deviation less than the population. How much less? Divide by the square root of n. Now, how large does your sample need to be in order for this to kick in? Even if you have a very skewed and funky distribution in your population, sample sizes of 10 and 20 can start to convert the population distribution into a very close to normal sampling distribution. So examples, let's work on some examples. So assume a school population of student heights are normally distributed around a mean of 1.4 and a standard deviation of 0.15 meters. This is the same information we were using in class the other night. Those numbers, the fact that it's normally distributed, the center and spread, those are for the population of students. They're for all individual students. So notice number 1, it asks about what's the probability a randomly selected student, single student. So that's talking about the population distribution. See the very slight change in the word for number 2. The probability of randomly selected, so far it's the same, but instead of saying a student singular, it says a sample of 16 students. That's a little different. If it's a single student, when we make the z-score, we would take the height minus 1.4, divide by the standard deviation, 0.15. But if we are doing a sample of 16, we would take the sample's average, 1.63, subtract 1.4. The difference is we don't just divide by square root of 0.15. This is the spread for individuals in the whole population. If we're doing a sample, then we need to divide in our z-score by 0.15 divided by the square root of the sample size, which is 16. And I wish I could show you on the screen. I might have to dub some in here at the end of me writing on the screen, because this is right now I'm on my main computer, not my nice fun Surface Pro that I can write on. Okay. So I'm going to do that, and I'll upload a little piece of me doing those by hand. Maybe I'll walk through all the examples that we did on the slides so that they're recorded. But I wanted to show you before I stop this recording in R. Now, the R component of chapter 4 is probably one of the smallest, other than the chapter on, let's see, what is it? Power is chapter 8. We don't even use R in chapter 8. But in chapter 4, I'm going to show you how to do this with the cancer data set. So the cancer data set has subjects that are getting either randomly assigned to treatment or control with different stages of cancer. So we've seen we can use furniture table 1. I think we've seen furniture's package function table 1. So this function or command that comes zipped in this furniture package, it will take the variable or variables plural that you put in its parentheses, and it will make a table where the variables are the rows, and then it will tell you either the mean and standard deviation if it's continuous, or count and percentage if it's categorical. So in this data set, we see we have 25 people in this data set, and the age variable has a mean of 59.6, I think this is years, and a standard deviation of 12.9 years. So this is just showing how to use a table. Now, we can use the scale command to convert a variable to its z-score. So in this second chunk of code over here, I'm showing creating the age, standardizing age, creating a z-score for age 2 different ways. This first line, both of them I'm using dply or mutate, but this first line I'm going to create the variable by taking the original variable, subtracting the average, the mean, 59.6, dividing by the standard deviation, 12.9. This is one way you can standardize. You can actually write the math. Make sure you use your parentheses, the age, whatever the variable's value is, minus the number that's the average in parentheses, and then divided by the standard deviation. So you can do that by hand. That's one option. Well, not really by hand, but you can write out the subtract and the divide. The shortcut that works equally well, will give you identical results, is to use the scale command. So inside the dply or mutate set of parentheses, inside of there, first you have to put the name of your variable you're creating, and I've added a z at the end. If you look really hard, you can see this top one I did a lowercase z, and the second one I did a big Z, because remember, capitalization matters in R. It sees these as 2 different variables, 2 different names, because the z. So this time I did it's equal to scaling at age. By default, the scale command will subtract the grand average, divide by the standard deviation. And then I've selected those variables and asked for just the head, the first few rows. So here's person number 1 in our data set is in the placebo group, and they're age 52 at the start of the study. Age is 52. Standardized with the subtract parentheses divide symbol gives us a negative 0.59. So they're more than a half a standard deviation below the average. And then the second one, the age with the capital Z, it's using the scale command, and you'll see it gets the exact same thing. So that is all that you need to know how to do out of chapter 4 in R. If you put it into table 1, here I've done table 1. Notice I've only done one version of creating the scaled score or the z-score. And when I did the table, notice the z-score. What's the average? If you do it right, this is one way to check. If you do a z-score correctly, the mean should be 0 and the standard deviation should be 1. And this is a way you can check it. And here I've taken that scaled score, that z-score, and I've done a histogram. Oh my. Oh, that was a slow developer. You'll notice the shape of this histogram. When you standardize a score, when you subtract the average and divide by the spread, you do not change the shape. This did not magically become a normal distribution. So I want you to be careful in this chapter to not confuse sampling distribution and standardizing a variable. We got S's going all over the place. Okay, so questions? Let me know. I'm going to check the discussion board as soon as I get this uploading. And then after I do some discussion boards, I'm going to take the questions up there and I'm going to make another recording that I am going to walk through the questions that are on the discussion board, as well as on my laptop, write out the show your work type way on those other problems to make sure that you guys can get those correct. So see you in the next video.